Want your program to repeat a task automatically? Stamping out the same action over and over without any manual intervention? That's exactly what the Java while loop does. We delegate these continuous actions to self-driving systems. But in software, we often hit a wall when using standard sequential programming, writing out every single step, one after the other. If you need to check a password or keep a game menu open, manually writing the code for 20 different attempts is unsustainable. The problem is unpredictability. You don't know if a user will enter their ATM PIN correctly on the first try, or if they'll mistype it 4, 5, or 6 times. You cannot hard-code a fixed number of attempts when the duration relies on an unknown human variable. To handle that uncertainty, we use the Java while loop. Instead of locking the computer into a fixed count of actions, this loop repeats a block of code based on a dynamic condition. It evaluates its environment in real time. Real-world logic requires this kind of flexibility. Hard-coded, rigid sequences break the moment an unexpected variable is introduced, which means our code has to be able to repeat itself dynamically to function. Take a look at this diagram mapping out a standard while loop. At the center, you have the condition, a true or false question. If the answer is true, the program routes down into the execution block to run your code. The crucial rule here is the order of operations. The program checks that condition before it does anything else. If the condition is false right from the start, the logic path skips the execution block entirely. Because of this strict pre-check mechanism, a while loop is capable of running 0 times. If the initial state doesn't meet the requirement, the door simply remains closed. This is a major departure from standard linear code. Normal sequential instructions execute blindly from top to bottom. They don't pause to ask if the current system state actually warrants running that particular piece of code. The while loop's condition acts as a strict barrier. It prevents any unauthorized execution, guaranteeing your code only runs when the specific environmental criteria you've set are actively met. Let's see this in motion by walking through a simple counting sequence. We want the computer to count numbers for us, step by step. Before the loop begins, we have a setup phase. We declare a starting variable, let's say a number starting at 0, and we initialize it in the computer's memory right outside the loop's gate. This tracking table shows our counter variable as we enter the execution phase. Since 0 is less than our target number, our condition evaluates to true, and the internal code block is cleared to run. At the end of that execution block sits the update phase. We mathematically modify our loop variable, adding 1 to it, and then route the logic back to the top to reevaluate the question. This cycle continues until the final iteration. Our updated variable finally crosses our target threshold. The condition evaluates as false, the barrier closes, and the cycle terminates. Automation relies on this internal logic to advance its own state toward a final resolution. But what happens to the internal logic if you write the loop but accidentally omit that critical update phase from the code? This diagram illustrates an infinite loop. Because the update step is missing, the variable never changes. The logic path circles through the execution block and never returns to the gate to reevaluate the exit condition. The physical consequences on your program are severe. Without an exit state, the system rapidly exhausts available memory, leading to frozen applications and system crashes. The power of infinite repetition is also a program's biggest vulnerability if the structural exit strategy is flawed. When structured correctly, the while loop elegantly handles complex continuous actions. It allows programs to wait in the background for a large file download to finish, or keep a game menu active until a player makes a choice. The primary rule for developers is simple verification. You must always ensure that your internal logic modifies a variable in a way that guarantees a future false condition, securing a safe exit from the loop. It comes down to 3 foundational pillars. The loop checks its logic before executing. It runs continually as long as that condition remains true. And depending on the initial state, it can execute 0 times or more. Compare that to the rigid manual coding we started with. Instead of hard-coding hundreds of repetitive lines, you achieve the exact same result with a clean, dynamic, and automated structure. Mastering the while loop provides the control needed to build software that responds to a changing environment. You have now acquired a foundational tool for professional Java programming. Picture a classic arcade machine sitting in a quiet room. The screen lights up, joysticks ready, and a new game waits for a player. In programming, we often face a specific puzzle. How do you write code that runs at least one time, no matter what? In Java, the answer is the do-while loop. Think about how you actually play. You drop in a coin, play through a level, and eventually the game ends. It's only at that point, after the action has finished, that the screen flashes a countdown, asking if you want to continue. Imagine if the machine worked the other way. If before you even touched a button, it asked, "Do you want to play again?" You couldn't answer that because you haven't played the first round yet. The machine lets the action happen first, and then asks for permission to repeat it. This sequence is the core logic behind the do-while loop. To see exactly how this looks in practice, we need to take a closer look at the underlying code logic. This is a standard while loop. It checks the rules at the very beginning. If the conditions aren't met right at the start, the program never moves to the action box. If our arcade machine used this logic, it might skip the game entirely, never giving a chance to start. The do-while loop is structured differently. It is written in two distinct parts. The top section is the do block. This is where you put your instructions, like the command to start the game. The bottom section is the while block. This contains the condition, which checks if the player wants to keep going. Because the condition check sits at the very end of the script, the instructions in the top block run before the program even considers stopping. Let's track a simple example. On the left is our code, and on the right is a memory box tracking a counter variable. The program enters the loop and immediately executes the action, updating our counter from 1 to 2. Only now does it reach the condition at the bottom. Since it is true, it loops back to the top to run again. But what happens if the player decides to quit after just one round? Even if the condition at the bottom is false the very first time the program checks it, the action at the top has already happened once. The program successfully performed its task before checking the exit rules. While this structure is incredibly helpful, it requires careful handling by the developer to avoid some common mistakes. The most frequent issue beginners face is creating an infinite loop. This happens when a programmer forgets to update the variable inside the loop. If the information the while block is checking never changes, the condition can never become false. Without a way for the condition to change, the program will repeat the action forever, which eventually causes the application to stop responding. To prevent this, always ensure that the code inside the execution block changes the variable being checked at the bottom. This structure is a useful tool for automation, but it relies on the developer to provide a clear path for the loop to eventually end. You can find this logic in many common applications we use every day. Restaurant ordering apps use this to show you the food menu first. The program displays your options before it asks you to make a selection. Secure login screens function similarly. The system must provide the login fields at least once, so you can enter your credentials before it checks if they are correct. Simple calculator apps use the same foundation. The program performs the calculation first, and then waits to see if you want to clear the screen or perform another task. In many menu-driven scenarios, the do-while loop provides a reliable way to ensure the user sees the interface before the program evaluates their next move. To wrap up, let's look at the three main characteristics of this loop. First, it is designed to run its code at least one time. Second, the program only checks the exit condition after the main action has already finished. And third, it is a practical choice for programs that rely on user interaction and menus. Understanding the do-while loop gives you greater control over user-driven applications and makes your Java programming skills even stronger. Need to repeat a task a specific number of times? The Java for loop is the perfect solution. But before we get to that, think about how you'd handle doing the exact same thing 100 times in a row. Your first instinct might be to just copy and paste the same line of code over and over. Programmers avoid that at all costs. Writing repetitive code creates a file spanning thousands of lines that is painfully slow to read. Worse, if you need to fix a single typo, you have to hunt it down and correct it 100 separate times. Imagine trying to manually type out individual attendance sheets for every student in a university, or updating the score on a stadium scoreboard displaying thousands of data points. Typing it out by hand isn't just slow, it's an invitation for mistakes. Instead, you can use a Java for loop. Think of it like an assembly line operated by a tireless, programmable factory robot. By using this loop, a tedious chore that would take hours to type out manually is transformed into a streamlined, automated process that happens in milliseconds. To get this digital factory working, we have to tell our robot exactly what to do. We do that by plugging 3 specific instructions into its control panel. The robot needs to know where the task starts, when the task should stop, and how to move on to the next item. First is the starting point, which programmers call initialization. We write this as int I equals 1. This simply creates a counter, starting at item number 1. Next is the stop boundary, known as the condition. If we write I is less than or equal to 10, we are telling the robot to keep working only as long as our counter hasn't passed 10. Finally, we need the update step. Writing I++ is a quick shorthand telling the loop to take a single step forward to the next item after it finishes a cycle. Let's watch this flow in action. The program starts the counter, checks to make sure it hasn't hit the stop boundary, performs its assigned task, moves the counter forward by 1, and then circles right back to check the boundary again. With every single cycle, you can see the variable I physically stepping upward, 1, 2, 3, keeping perfect track of exactly where the program is. Packing the starting point, the stop boundary, and the step forward into a single structure gives you precise control over exactly how your software behaves. Because of this precision, you can generate complex outputs almost instantly. If you need to print a multiplication table reaching into the thousands, the loop handles the math and the formatting for you. You can also use it to quickly tally up the total sum of a financial ledger with 1 million entries, or accurately count items across a global digital inventory. But there is a catch. What happens if you give the control panel a stop condition that is mathematically impossible to reach? You create what is known as an infinite loop. The program gets trapped in a dangerous, never-ending cycle, consuming your processing power until it causes the application to freeze and become unresponsive. This usually happens when a beginner makes a simple typing mistake, like accidentally telling the counter to step backward instead of forward, moving it further and further away from the stop boundary. This is why choosing the right tool matters. While the for loop is perfect for when you know the exact number of steps, Java also offers while loops for situations where the finish line is unpredictable, like waiting for a user to finally click a button. Knowing your stop condition is the key. When you have a clear finish line, the for loop provides the most stable and readable structure for your code. Let's step back from the factory metaphor and look at the actual code on a clean screen to see what we've built. The core takeaway is simple. The for loop is your best choice for known iterations. Its biggest advantage is readability. It neatly combines your start, stop, and step commands into one single organized line of code. That clean layout makes it one of the most commonly used tools in the Java language. By understanding how to write this one simple line, you turn what would be an overwhelming, labor-intensive coding chore into a fast, manageable tool. Master the for loop, and you'll write cleaner, faster, and more efficient Java programs. Want an easier way to read every single element in an array without all the hassle? Meet Java's enhanced for loop. Imagine a teacher managing a classroom grading system. They need a program to sequentially read through a digital list of student names and their corresponding marks. Historically, a traditional for loop divides logic into 3 manual parameters. You initialize a counter, check the index against the array's length, and manually increment it. A small mistake, like using less than or equal to, causes a crash with an array index out of bounds exception. While these loops are powerful, they require a lot of boilerplate code just to read a list from start to finish. This creates a need for a tool that handles those iteration steps automatically. Java's solution to this verbosity and the risk of indexing errors is the enhanced for loop, often called the for each loop. The 3-part manual setup of the traditional loop compresses into a 2-part syntax, separated by a single colon. To the left, you declare a temporary variable holding the specific item accessed. To the right, you provide the target collection or array to traverse. This shift means you no longer have to track the indexed or check the array's boundaries. The Java compiler takes over those responsibilities entirely. Let's look at how this works internally, using an e-commerce product list as our dataset. Under the hood, Java automatically handles bounds checking. It extracts the first element and assigns it to a temporary variable, without needing a numerical index. Once finished, it automatically moves to the next element. This cycle repeats until reaching the end of the collection. This process is highly flexible. As you can see here, the exact same syntax works whether you are iterating over a standard fixed-size array or a dynamic array list. This provides a standardized way to traverse data structures, ensuring your method for reading a list remains the same regardless of how it is stored. It is important to remember that this is a specialized tool, not a complete replacement for traditional loops. Because the iteration is automatic, you can only move forward through the data. You cannot use this loop to iterate backward or skip specific elements. Since the index is hidden, you also don't know the position of the item you're reading. If your logic depends on knowing that an item is at index 5, this loop won't provide that information. There is also a specific error to avoid. You cannot add or remove items from a collection while the loop is running. Doing so will immediately trigger a concurrent modification exception. The general rule is to use this loop strictly for reading data, rather than modifying the structure of the list itself. By following these practices, you can simplify your code and remove the risk of manual indexing errors. It provides a clean, unified way to handle arrays and collections. The enhanced for loop makes Java code simpler, cleaner, and more readable. What happens when one loop runs inside another? Well, that is the awesome tower of nested loops in Java. To understand why we need them, we have to look at how we normally process data. A standard single loop moves in a straight line. It reads a flat list of names from top to bottom, or simply counts from 1 to 10. But the real world rarely operates in a straight line. Data is rarely flat. Programmers constantly navigate multi-dimensional spaces. Think about a digital calendar tracking weeks and days, a ticketing system managing theater seating by rows and individual seats, or the coordinate grid of a standard game board. If you try to move across a complex grid like that with a linear loop, you stay trapped on a single line. To navigate the entire board, we have to introduce a new dimension of logic. We place one loop directly inside another. In Java, this structure relies on two distinct parts, the outer loop and the inner loop. Together, they follow a strict mechanical rule. For every single step the outer loop takes, the inner loop must run its entire life cycle, from start to finish. Looking at this matrix traversal, you can see how they divide the labor. The outer loop is in charge of the y-axis. It moves down the grid, row by row. Once the outer loop locks onto a row, the inner loop wakes up. It handles the x-axis, scanning across every individual cell in that specific row, column by column. Only when the inner loop reaches the end of the row does its job finish. The outer loop then ticks down to the next row, and the inner loop starts all over again. This synchronized, alternating X and Y scanning process is what guarantees a program can systematically touch every single piece of data hidden inside a two-dimensional space. We can apply this exact logic to generate mathematical outputs. This grid demonstrates a multiplication table. The code simply multiplies the current outer loop value by the inner loop value. 1 times 1, 1 times 2, 1 times 3. The inner loop finishes, the outer loop increments its multiplier to 2, and the next row of the table writes itself. We can also shift from mathematics to visual generation. This precise coordinate system is how programmers print complex shapes and patterns out of text. By placing conditional if statements inside the inner loop, you give the program instructions to selectively choose exactly when to print a character and when to print an empty space. Whether you are populating a grid of multiplication results or rendering a visual shape on screen, nested loops turn simple repetition into a coordinated two-dimensional output. At this point, you have the conceptual tools to break free from flat data and process multiple dimensions. But we have to look at this chart to understand the cost. Computer scientists tracked how long an algorithm takes to run, a metric called time complexity. A single loop gives you this flat line. But nested iteration triggers the multiplier effect, causing an exponential spike in execution time, known as O of n squared. Here is the hard math. Traversing a tiny grid of just 100 rows by 100 columns requires 10,000 distinct operations. This density creates room for error. The most common mistake new coders make is accidentally mixing up their inner j and outer I variables, causing the code to read the wrong data or trapping the program entirely in an infinite, endless loop. Because of that exponential increase in work, nested loops require careful consideration. They are the primary tool for multidimensional data, but they must be used with an eye on performance. So remember the core concept: one loop inside another. They are used specifically for patterns and multidimensional data. Mastering this nested logic provides the foundation for handling everything from data matrices to spatial algorithms. What exactly happens when one loop runs entirely inside another? That interaction is the defining power of nested loops. A standard Java loop is built for linear efficiency. It handles one-dimensional tasks like counting numbers or reading through a flat list with minimal overhead. But because these loops only move in one direction, they reach a functional limit the moment your data becomes more complex. Linear code cannot effectively navigate or map data that exists in more than one dimension. Think about how we organize information in the real world. Digital calendars, theater seating charts, and game boards all rely on a grid structure. A single loop can iterate across a row or down a column, but it cannot track both movements at the same time. This creates a structural problem. How can a program expand its reach to process vertical and horizontal coordinates simultaneously? To manipulate a two-dimensional space, the structure of our code must mirror the dimensions of the data it intends to process. Nested loop syntax provides that second dimension. It is quite literally one loop placed inside the body of another. We assign each loop a specific responsibility. The outer loop manages the vertical movement between rows, while the inner loop manages the horizontal movement across columns. The core rule is this: for every single step the outer loop takes, the inner loop must complete its entire cycle. During execution, the outer loop locks on to the very first row. Then the inner loop fires, processing every single column in that row until it reaches the end. Once the inner loop is exhausted, control returns to the outer loop, which steps down to the next row and triggers the cycle all over again. This sequence, one step on the outside for a full cycle on the inside, is the mechanical basis for multidimensional data processing. We can see this in action when generating a multiplication table. The code calculates and fills in the products row by row as the inner loop sweeps across. This row-by-column logic is the standard method used to locate or modify any data point within a matrix. It also allows for pattern printing. By making the inner loop's limit dependent on the outer loop's current position, we can generate specific geometric shapes. On row 3, the outer loop tells the inner loop to run exactly 3 times, creating a row of 3 asterisks before moving to the next line. Mastering this execution flow transforms basic linear counting into the ability to generate and navigate structured two-dimensional layouts. While nested loops allow us to organize data across multiple axes, this structural power has a direct impact on performance. We measure this impact through time complexity, which tracks how the number of operations grows as we add more data. This graph shows the workload multiplier. If both your outer and inner loops run 10 times, the computer must execute 100 total operations. Redundant or poorly designed nested loops can significantly slow down a program or cause it to hang by forcing the processor to perform thousands of unnecessary iterations. Before nesting a loop, always determine if the data problem can be solved by flattening the structure or using a more efficient algorithm. However, for generating patterns and traversing multidimensional arrays, they remain an essential architectural tool. Understanding the mechanics of nested loops provides the necessary foundation for tackling complex matrices and high-level data processing. Want to stop a loop immediately? The Java break statement makes it possible. Computers execute instructions relentlessly, even when that obedience wastes resources. Imagine a for loop searching an array of 1 million database records for a single profile. It finds the target at block 5 instantly, but without explicit instructions to stop, the machine continues grinding through the remaining 999,995 records, wasting processing power and memory. The Java break statement acts as a precise override tool for this scenario. The moment your code triggers a break command, it instantly exits the control structure it's currently running in. This allows the program to move to the next task the moment the loop's condition is satisfied, avoiding redundant iterations. The syntax requires just the word break followed by a semicolon. We see this used in flat control structures, like an application's user interface. A Java switch statement evaluates a user's input and directs the logic down a corresponding path, such as start, settings, or quit. Switch statements have a behavior called fall-through. If a user selects Settings, the code executes that block, but then cascades downward, triggering Quit and every other option below it because it lacks a stopping point. Placing a break command at the end of a switch case isolates that choice. The execution hits the break, immediately exits the switch, and continues with the rest of the program. This creates a boundary that ensures a specific user command triggers only the intended logic and nothing else. This principle extends from flat menus into dynamic single-loop environments. Whether you are running a while, a do-while, or a for loop, the mechanic remains the same. In a basic search algorithm, the execution path enters a while loop, evaluates the condition, runs the block, and cycles back to the top. The instant an internal condition is met, the break command triggers. The cycle terminates, and the execution line jumps to the code following the loop's closing bracket. A common mistake is placing the break statement in the wrong scope. If the break is triggered by the wrong logic gate, it can stop a search before the target data is actually found. Another error is creating unreachable code by placing commands immediately after a break within the same block. Because the break causes an immediate exit, the Java compiler knows those lines can never execute and will flag them as an error. Understanding loop scope and the sequence of execution allows you to use these breaks to create precise, targeted search algorithms. Targeting becomes more complex in multidimensional spaces. In a game engine, for example, the program calculates collisions on a 2D coordinate grid. To track this, the engine uses a nested loop. The outer loop scans the vertical y-axis, while the inner loop cycles through the horizontal x-axis for every vertical step. If a collision is detected and a standard break triggers, the program only escapes the inner x-axis loop. It remains stuck circulating within the outer y-axis loop, which can delay the game's response to the event. Java provides a solution through the labeled break. By adding a text identifier to the outer loop, the break command targets this identifier. Upon collision, the execution bypasses both layers of logic and exits the entire nested structure instantly. As the environment becomes more complex, labeled breaks serve as a direct path to the next logical layer of the program. The break statement adds a layer of conditional logic to your loops, allowing you to stop a process the moment it's no longer necessary. This chart compares resource usage between a standard loop and one using a break. The optimized loop on the right shows a smaller footprint because it exits immediately, saving millions of unnecessary iterations. When applied across thousands of background operations, these micro-optimizations improve the overall speed and responsiveness of your software. Knowing when to use break helps you write smarter and more efficient Java programs. What if you want to skip a single loop iteration without stopping the entire process? That is the specific role of the continue statement. Imagine a program processing thousands of entries. You hit a point where the data is irrelevant. Perhaps it's an invalid input or an even number in a sequence where you only need the odds. Using a break statement here is destructive. It acts like an emergency stop button, killing the loop immediately and discarding every valid data point that was still waiting to be processed. You could try to filter this data using nested if-else blocks. While this works, it adds layers of indentation that make your logic harder to follow and your files heavier to read. Instead, the continue statement provides a way to bypass unwanted data points while keeping the rest of the processing cycle running. The continue statement uses a simple one-word syntax followed by a semicolon. Track the execution path through the loop body. It encounters the continue keyword inside a conditional check. Instantly, the compiler ignores the remaining code in that block. It jumps back to the top to begin the next iteration. Essentially, continue serves as a reset trigger. It ends the current cycle early so the machine can immediately move to the next piece of data. In a loop from 1 to 10, continue filters out even numbers. 2, 4, and 6 are rejected, while odds pass to the output. Crucially, the execution path first jumps to the update statement, the I++, ensuring the counter keeps moving forward. This logic also applies to while and do-while loops. This is useful when you are checking user input and need to skip over entries that don't meet your formatting requirements. The difference here is the destination. Since while loops don't have a built-in update step in the header, the continue statement sends the execution straight back to the Boolean condition check. Regardless of the loop structure, the statement functions as a gatekeeper, filtering out specific values to protect the core logic of your program. Let's compare two identical loops side by side. On the left, a break statement terminates the entire cycle, exiting the loop completely and leaving remaining data unprocessed. On the right, continue sidesteps the current block, looping back to the top to process the rest of the dataset. In short, break is for termination, while continue is for filtering. While this filtering is efficient, it does introduce a risk, the infinite loop trap. This happens in while loops if you trigger a continue statement before you update your counter variable. Because the counter never changes, the program evaluates the exact same state over and over, causing the application to hang. Using continue requires you to be deliberate with your loop control variables to ensure the program can always progress to the next state. By using continue instead of deep nesting, you keep your code flat and readable, which makes it much easier for other developers to understand your logic. To recap, the continue statement skips the current iteration, moves immediately to the next one, provides a clean way to filter data, and improves the overall readability of your loops. Master the continue statement to make your Java loops more flexible and efficient. Using these control flow tools allows you to handle complex data streams with the precision required for high-quality software development.